7. It's called Linearizing Data to Find Models. We're going to be looking at a set of data and trying to understand what kind of model it comes from. Now, this particular section has several models. We are only going to be specifically looking at the exponential model. So even though if you look in the textbook, which you might have soon since we ran out of time today, you might see other models. We're not going to get into all those models, so don't panic. We're only going to be looking at one of them. The big question when you look at a set of data is, does this model come from an exponential model? What did we use to measure the strength of a linear correlation? So we used the correlation coefficient. Yes, that starts and ends with the letter R. And what was the biggest value it could possibly be? 1, right? Is that a good thing or a bad thing? That's perfect, right there. What was the lowest value? -1. That also was a perfect value. Perfect correlation. This had a negative slope. And this had a positive slope. Hush. Yes. Fourth period doesn't understand what's going on at the moment. If the correlation coefficient is 0, then there is no linear correlation between the two variables. Now, it could be some other kind of correlation, or there could be random points all over the place. But these are the two perfect values. We would really like to know if, now correlation does not belong to the exponential model. So the idea of linearizing this set of data is to see if we can find out if this data did come from an exponential model. In other words, what we're going to do is we're going to straighten this thing out. And based on the operation we choose, then we'll know whether it was exponential. So, how do we linearize? Now, you already know how to do this. Okay, we've done it on quizzes, practice quizzes, tests. We did it in the notes, so you've already seen this. What did we do to the left side of this? We did a common logarithm. Okay, in other places we did a natural log, but it really doesn't matter. The same process holds true. So we have a common log of y, so we must do the same thing to the other side. All right, so there's a product, and we need to split it up. So we have log y equals log a plus log b to the x. Now, what can we do with the x? Move it down in front, right? Make it a coefficient. So we have log y equals log a plus x times log b. I know that kind of squeezing this in here, but we've got mx plus b equals log y. It's your linear form, mx plus b, where log a represents the y-intercept and log b represents the slope. Now, I need you to use your calculator and get this list of data entered in your calculator right now. Into list 1 and list 2. All right, so now we got the data entered in our calculator. These are years after 1900, so this would be 1982, 1983, and so on. This information was recorded from the U.S. Health Department. These are reported AIDS cases. We want to know if this data came from an exponential model. So in list 3 in your calculator, I want you to take the logarithm of the y value. So go up to the top of list 3. Ooh, this is really, I'm trying to find a good spot on screen here, and it's not really working. Okay, that's about the best I can do. Sorry. Okay. We're going to take the logarithm. Where are the y values? They're in list 2, so we want log L2. You'll see that at the bottom of the screen, log L2. Wow, this is really hard to do on this screen. Man, I wait till my other machine comes back. All right. It doesn't help. I either have a problem with the lighting for you guys or the lighting on camera. Okay, so we have our x values here, and we have our log of our y values in list 3. We did log L2. Now, it'd be really nice if I could do the linear regression of list 1 and list 3. So I'm comparing these two lists, and I'm saying, are these two linear? Because if these two are linear, then the original ones are exponential. So how do you do that linreg thing on your calculator? Okay. Stat, okay. Stat, calculate, all right. And then the fourth one in the list, linreg. All right, now please make sure you give it list 1, comma, list 3. Otherwise, it defaults to list 1 and list 2. And that's not what we want the linear regression of. Now we'll get a particular set of values here. Can you tell me, do you understand, I should say, that the left side of the equation is not y equals, it's log y equals. Right, so you have the 0.342x, oops, sorry, can't write, 0.342x minus 25.318. That is the linearized form of this equation. Okay, what was the correlation coefficient? R. We don't want r squared. We want the value of r. All right, 0.98. We'll guess we'll go 988. Good or bad? That's pretty good. That's a strong positive correlation. Now, the last thing we would need to do, since we're convinced that this is from an exponential model, because the log of the y values and the x's create a linear function with a strong positive correlation, and it wouldn't matter if it was strong negative, that'd be okay as well. We need to change it back to its exponential form. So how do we change this function back to its exponential form? What's the base of the logarithm? 10, right? We're going to do that swooshy swoosh thing, right? 10, there's your exponent equals y, right? So 10 to the y, 10 to the 0.342x minus 25.318 equals y. We've done examples like this even in problems in class. We talked about using your algebra. I'm going to reverse this, put the y on the other side. When you are adding exponents together, that is the same as what? Multiplying like bases is what I'm talking about. So these two things are going to be equivalent. Adding exponents is the same thing as if I would say 10 to the negative 25.318 times 10 to the 0.342x. Now, when you multiply bases, that's the same thing as the power of a power property. Now, it should become fairly evident what the exponential form looks like. Remember, y equals ab to the x? Well, that must mean that a is equal to 10 to the negative 25.318. If you type that on a calculator, you're going to find that's a really nasty looking number. So I wouldn't mess with it. I think I would just leave it as 10 to the negative 25.318. B, if you type 10 to the 0.342 in your calculator, you'll find out that's approximately 2.198. So the exponential model that we have here is 10 to the negative 25.318 times 2.198 to the x power. I know I'm running out of room there, but I'm sure you can write that in your notes. Now, let's understand, why is this number so small? X represents the number of years after 1900. That number is so stinking small because that's the starting amount. That's the number of AIDS cases recorded in the year 1900, according to the model. Obviously, probably not going to be a very big number, since that was a more recent disease. But I also noticed that we are more than doubling every single year. That's not good. So the U.S. Health Department looked at this information and started making decisions about education and how money is spent and resources to find cures for this particular disease. That's linearizing your data. Taking the logarithm of the y values, taking the ln reg of the x's and the new log y values, then seeing if the correlation coefficient is a strong one. Once you decide it's a strong one, then convert it back to its exponential form.